Hello, in this lecture we'll find out the area of the green shape. In the drawing we have a quarter circle, AOB is a quarter circle. We know that side OB equals to 2 units in its length, and line segment AD equals to line segment DO. And our mission is to find out the area of this green shape. We also know that angle DCB equals to 90 degrees in its size. Therefore, the green shape, it is actually the right triangle DCB. So, in other words, our mission is to find out the area of this green right triangle DCB. Okay. So, first of all, we know that AOB is a quarter circle. Therefore, this angle AOB must be equal to 90 degrees in its size. In addition, because of the fact that AOB is a quarter circle, AO and OB, they are both the radii of this quarter circle, but we know that OB equals to 2 units, therefore the radius of this quarter circle equals to 2 units in its length. And AO is also the radius, therefore AO must be also equal to 2 units. AO equals to 2. We know that AD equals to DO, and AD plus DO equals to AO, that is 2. So if we define the line segment AD as X, then line segment DO must be also equal to X because they are equal to each other according to what is given as the question. So AD, that is X, plus DO, that is also X. In total, this equals to AO, but AO is 2. Therefore, X plus X equals to 2. X plus X equals to 2. So X plus X is 2X, and 2X equals to 2. Here we divide this equation by 2, and finally we get that X equals to 2 over 2, that is 1. So AD is equal to X equals to 1 unit in its length. And DO, that is also equal to X, it is also equal to 1 unit in its length. In the next step, I copy the white triangle ODB in a new page, and we will implement the Pythagoras theorem on this white triangle ODB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is a version for Pythagoras theorem. So actually, this is the right triangle DOB that I copied from the original drawing. According to the Pythagoras theorem, this right triangle DOB, DB squared equals to DO squared plus OB squared. So I write it down. The square of the hypotenuse is DB squared, and it must be equal to DO squared plus OB squared. DB is the missing side, so we leave it as it is. So DB squared equals to DO squared. DO is 1, therefore DO squared is 1 squared, that is 1, plus OB squared. OB is 2, therefore OB squared is 2 squared, that is 4. So in total DB squared equals to 1 plus 4, that is 5. DB squared equals to 5. We take a root out of this equation and finally we get that DB equals to the square root of 5 units. So actually, this is side DB and it is equals to the square root of 5 units in its length. In the next step, we'll do a construction, that is to say, we'll complete this quarter circle to a circle. So, completed this quarter circle to a circle. In the next step, we'll extend the radius BO by straight line until it touches the circle. Actually, BO is the radius of the circle, therefore it is absolutely a straight line. When you extend the straight line by straight line, the result must be a straight line. Here we define the touching point of the extended radius BO with this circle, this point as point P. We extended the straight line BO by straight line and the result is BP. Therefore BP must be also a straight line. So if we focus on the upper side of this straight line BP at point O, here the sum of the angles must be equal to 180 degrees according to rule 3, that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of BP at point O? We have this angle that is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. We already found out that BP is a straight line, but BP is a straight line that touches the circle at 2 points, B and P. Any straight line that touches the circle at 2 points must be a chord. So BP is a chord, but BP is a chord that passes through point O, that is the center of the circle. And we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, BP is the diameter of the circle. So write it down. We found out that line segment PB is the diameter of the circle. It is given us the equation that angle DCB equals to 90 degrees in its size. In the next step, we will extend side CD by side line until it touches the circle. By extending line segment CD until it touches the circle, we create peripheral angle. And this peripheral angle equals to 90 degrees in its size. According to rule 5, any peripheral angle that is equal to 90 degrees in its size must be subtended on the diameter of the circle. Repeat again on rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees in its side must be subtended on the diameter of the circle. Here we have peripheral angle MAN that is equal to 90 degrees inside. Therefore, this peripheral angle must be subtended on the diameter of the circle. Here, MN is the diameter of the circle, and indeed, this peripheral angle MAN that is equal to 90 degrees in its size is subtended on MN, that is the diameter of the circle. We can implement rule 5 in our drawing because we have this after we extend side CD until it touches this circle, we create a peripheral angle, and this peripheral angle is equal to 90 degrees in its side, therefore it must be subtended on the diameter of the circle. The diameter of the circle is PB. And therefore, when we extend the side line, this CD by side line, it must touch the circle at point P and only at point P. Otherwise, it will contradict rule 5 because we have peripheral angle that is equal to 90 degrees in its size and still it doesn't subtend on the diameter of the circle, that is PB. The only way that peripheral angle, this peripheral angle is equal to 90 degrees in its size will be subtended on the diameter of the circle is that the line segment CD, after we extend the line segment CD by side line, it must touch the circle at point P. Otherwise, we will get contradiction to rule 5. Okay, so here, peripheral angle CD must touch the circle after we extend side CD. Side CD must touch the circle at point P and at point P only. And here we have peripheral angle BCP that is equal to 90 degrees in its size, and indeed it's subtended on PB, that is the diameter of the circle. Otherwise, if the extended side CD doesn't touch the circle at point P, for example, if it touches the circle at this point, we'll get here peripheral angle that is equal to 90 degrees in its size, and still it doesn't subtend on the diameter of the circle, in contradiction to rule 5. Okay, in order to avoid the contradiction, the extended side CD must touch the circle at point P and at point P only. And here I repeat again that we have peripheral angle BCP that is equal to 90 degrees in size, and it's subtended on PB, that is the diameter of the circle. So here in the drawing, actually, it obeys to rule 5 that we have peripheral angle that is equal to 90 degrees in size and it's subtended on PB, that is the diameter of the circle. So in the next step, we extend the radius AO by a straight line until it touches the circle. And we define the touching point of the extended radius AO with this circle. This point is point Q. What is the definition of line segment OQ? Line segment OQ starts from point O, that is the center of the circle, and then at point Q, that is the point on the circle itself. So this is exactly the definition of a radius. Therefore, OQ is the radius of this circle that is equal to 2 units. In the next step, I'll copy, actually, I don't have to copy the right triangle DOPO because we already found out that the right triangle DBO, we have side DO that is equal to 1 unit in its length, side OB equals to 2 units in its length. Here we have the same triangle because we have side DO that is equal to 1 unit in its length. What is the length of side PO? Side PO starts from point O, that is the center of the circle, and that's at point P, that is the point of the circle itself. So this is exactly the definition of a radius. Therefore, OP is the radius of the circle that is equal to 2 units in its length. So we have in this right triangle ODP, one side equals to 1 unit in its length, the other side equals to 2 units in its length. Exactly like this right triangle DOB, this side equals to 1 and side OB equals to 2, and the hypotenuse equals to square root of 5. Therefore, the hypotenuse of this right triangle PDO must be also equal to square root of 5 units in its length. Okay, you can actually say that those two right triangles can go into each other according to side angle rule. You have the side DO, this is the common side OB equals to side PO, they're both the radii of the second, therefore they're equal to each other, and those two angles are both equal to 90 degrees, therefore they're equal to each other, so those two right triangles can go into each other according to angle side angle side rule, and therefore all the sides of the right triangle DOB must be equal to the sides of the right triangle DOP, therefore the hypotenuse DP equals to the square root of 5 units, therefore the hypotenuse PD also equals to the square root of 5 units. Anyway, even according to the Pythagoras theorem, we get that the hypotenuse PD of this right triangle must be equal to the square root of 5 units in step, because we have the same perpendiculars 2 and 1. Therefore, according to the Pythagoras theorem, if we have the same perpendiculars, then the hypotenuse must be also the same, that is square root of 5. Okay, so in the next step, we will implement on this drawing rule 11. Repeat again on rule 11. According to rule 11, in any circle, if chord AB intersects with chord CD at point O, then the following equation will be true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can actually implement rule 11 in our drawing. Why? Because in our drawing we have, this is chord AQ that intersects with chord CP. This is chord CP at point D. Again, chord AQ intersects with chord CP at point D. So I write it down. Chord AQ intersects with chord CP at point D. Repeat again. In our original drawing, chord AQ intersects with chord CP at point D. Therefore, the following equation will be true according to rule 11. AD times DQ equals to CD times DP. AD times DQ must be equal to CD times DP. But again, according to rule 11, we know that AD times DQ equals to CD times DP. AD equals to 1 times DQ. DQ in total equals to 1 plus 2, that is 3. And it is equals to CD. CD is the missing side, so we leave it as it is. Times DP. DP equals to the square root of 5 units instead. Actually, according to rule 11, we found out that 1 times 3 equals to CD times square root of 5. So 1 times 3 is 3, so 3 equals to square root of 5 times CD. Here we divide this equation by square root of 5. And we get that according to this equation, CD equals to 3 over square root of 5 units in its length. So this is side CD and it is equals to 3 over square root of 5 units. So write it down, CD equals to 3 over square root of 5 units in its length. In the next step, I copy the right green triangle DCB in a new page and we will implement the Pythagoras theorem on this right green triangle DCB in order to find out the missing side CB. Here by PT is a version for Pythagoras theorem. So actually, this is the right triangle DCB, this is according to the original drawing. Actually, our mission is to find out the area of this right triangle. So here we implement the Pythagoras theorem on this right triangle DCB. According to the Pythagoras theorem in this right triangle DCB, the square of the hypotenuse is dB square. So dB square must be equal to CD square plus CB square. The hypotenuse dB is square root of 5, therefore dB square is square root of 5 squared, it is 5. And it is equals to CD square. CD is square root of CD is 3 over square root of 5, therefore CD square is 3 over square root of 5 square plus CB square. CB is the missing side, so we leave it as it is. So 5 equals to 3 over square root of 5 square equals to 3 squared, that is 9 over square root of 5 squared, that is 5. So in total this expression equals to 9/5 plus CB square. Here we subtract 9/5 from this equation and we get that 5 minus 9/5 equals to CB square. So here we multiply 5 by 9, we multiply 5 by 5 and then we divide them by 5 in order to overcome a factor with 9/5. So 5 times 5 is 25, so in total in the numerator of this expression we have 25 minus 9 divided by 5. And it is equals to CB square. So we found out that 25 minus 9 is 16, so in total this expression equals to 16 fifths. That is equals to CB squared. So if I found out that CB squared equals to 16 fifths, here we take all the order of this equation, and finally we get that CB equals to the square root of 16, that is 4 over square root of 5. So CB equals to 4 over square root of 5 units in its length. This is side CB, this is equals to 4 over square root of 5 units in its length. In the next step, I copied this green right triangle DCB in a new page, and we find out the area of this green right triangle DCB. That is the area that we are looking for in this question. Actually, this is the right green triangle DCB that I got from the original drawing. So what is the area of this right triangle DCB? Actually, the area of any triangle equals to the base of the triangle times the height to the base over 2. And the area of this right triangle DCB, it is actually the area of this green shape. Because the area of the green shape, it is actually the area of the right green triangle DCB. Therefore, we can write down that the area of the green shape equals to the base of triangle DCB. We choose the bases DC times the height. The height must create 90 degrees with the base, and CB creates 90 degrees with the base CD, because this angle equals to 90 degrees. So the height is CB over 2. So we have this right triangle DCB equals to DC. DC is 3 over square root of 5 times CB. CB is 4 over square root of 5 divided by 2. So here we have 3 times 4 is 12. The square root of 5 times square root of 5 is 5 divided by 2. So here we have 12 over 5 over 2. 12 over 5 over 2 is equals to 12 over 5 times 2. So it is equals to 12, and 5 times 2 is 10. So it is 12 over 10. Here we divide both the denominator of this number by 2. 12 over 2 is 6, and 10 over 2 is 5. So the total area of the green shape equals to 6 fifths square units, or in terms of numbers, 6 fifths is 1.52 square units. Repeat again, the area of this green shape equals to either 6 fifths square units, or in terms of numbers, the area of this green shape equals to 1.2 square units. So in the next step, I will summarize the lecture. In this lecture, we shall found out the area of this green shape. So in the drawing we have a quarter circle, AOB is a quarter circle, side OB equals to 2 units in itself, line segment AD equals to line segment DO, this angle equals to 90 degrees in its size. Our mission is to find out the area of this green shape. Because of the fact that angle DCB equals to 90 degrees in its size, actually our mission is to find out the area of this green right angle DCB. Okay. So first of all, it is given us the question that AOB is a quarter circle, therefore angle AOB must be equal to 90 degrees in its size. In addition, AO and OB, they are both the radii of this quarter circle, therefore they are equal to each other. But it is given us the question that OB equals to 2, therefore the radius of this quarter circle equals to 2 units in its length, and therefore the radius AO is also equals to 2 units. It is given us the question that AD equals to DO. If we define AD as x, then if we define AD as x, then DO must be also equal to x because they are equal to each other. AD plus DO equals to AO. AD is x, DO is x, therefore AD plus DO is x plus x. So x plus x equals to AO, that is 2. Wait again, x plus x equals to AO, that is 2. X plus x is 2x, so 2x equals to 2. Here we divided this equation by 2 and found out that x equals to 2 over 2, that is 1. So AD that is equal to x equals to 1, and DO that is also equals to x equals to 1. In the next step, I copied the right white triangle DOB in the new page, and we implemented the Pythagoras theorem, this right white triangle DOB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This is the right triangle DOB, that I copied from the original drawing. The hypotenuse in this right triangle DOB is DB, therefore the square of the hypotenuse is DB square, and DB square must be equal to DO square plus OB square. DB is the missing side, so we leave it as it is, so DB square equals to DO square. DO is 1, therefore DO square is 1 square, that is 1, plus OB square. OB is 2, therefore OB square is 2 square, that is 4. So in total, DB square equals to 1 plus 4, that is 5. DB square, the square of the hypotenuse DB square equals to 5. Here we took a root out of this equation and found out that DB, the hypotenuse DB, equals to the square root of 5 units in its length. So here this is side DB that equals to square root of 5 units in its length. In the next step, we did the construction. That is to say, we completed this quarter circle to a circle. And then we extended the radius BO by a straight line until it touches the circle at this point. We define the touching point of the extended radius BO with this circle, this point is point P. BD is a radius, it is absolutely a straight line. We extended the straight line BD by a straight line, and therefore the result must be a straight line. The result is BP, that must be also a straight line. So we know that BP is a straight line, so if we focus on the upper side of this straight line BP at point O, here the sum of the angles must be equal to 180 degrees according to the rule 3, that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of BP at point O? We have this angle that is a right angle plus the missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. We have already found out that BP is a straight line, and here BP is a straight line that touches the circle at 2 points, P and B. Therefore, BP is a chord, and BP is a chord that passes through point O, that is the center of the circle. And we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, POB is the diameter of the circle. If POB is the diameter of the circle, it means that PB is also the diameter of the circle. Here, note down that PB is the diameter of the circle. In the next step, I extended side CD by straight line until it touches the circle. It is given us the equation then this angle equals to 90 degrees in size. After we extended side CD by straight line until it touches the circle, we created a peripheral angle. This peripheral angle equals to 90 degrees in size, and therefore according to rule 5, any peripheral angle that is equal to 90 degrees in its size must be subtended on the diameter of the circle. And PB is the diameter of the circle, and therefore peripheral angle, this peripheral angle that is the right angle, it must be subtended on PB, that is the diameter of the circle. The only way that the peripheral angle, this peripheral angle that is equal to 90 degrees in size, will be subtended on the diameter of PB is that the extended side CD will touch the circle at point P. Otherwise, the extended side CD, if the extended side CD doesn't touch the circle at point P, we will have contradiction to rule 5. Why? Because if the extended side CD will touch the circle at this point, it means that we have a peripheral angle that is equal to 90 degrees in its size, and still it doesn't subtend it on the diameter of the circle. In order to avoid the contradiction, we must conclude that the extended side CD must touch the circle at point P and only at point P and not in any other point. So we have here peripheral angle BCP that is equal to 90 degrees in its size, and it obeys to rule 5 in the sense that it's subtended on the diameter PB of the circle. Okay. In the next step, we extended the radius BO. What is the already extended radius BO, of course, by straight line, and what is the definition of line segment OP? Line segment OP starts from point O, that is the center of the circle, and then at point P, that is the point of the circle itself. So this is exactly the definition of radius. Therefore, OP is the radius of this circle that is equal to 2 units in its length. So we have in the right triangle DOB, we have one side that is equal to 1, the other side OB equals to 2, and therefore the diameter is equal to 3. In the right triangle DOB, we also have the same side DO is equal to 1, side OP equals to 2, therefore the hypotenuse must be also equal to 5 units in its length according to the Pythagoras theorem. So dP equals to the square root of 5 units in its length. In the next step, I extended the radius AO by straight line until it touches the circle. We define the touching point of the extended radius AO with this circle, this point as point Q. What is the definition of line segment OQ? Line segment OQ starts from point O, that is the center of the circle, and then at point Q, that is the point of the circle itself. So this is exactly the definition of a radius. Therefore, OQ is the radius of this circle, that is equal to 2 units in its length. Here we can implement rule 11. Repeat circle on rule 11. According to rule 11, rule 11 is true in any circle. So in any circle, if chord AB intersects with chord CD at point O, then the following equation will be true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can actually implement rule 11 in our drawing. Why? Because we have in our drawing chord AQ. This is chord AQ that intersects with chord CP. This is chord CP at point D. Repeat again. In our original drawing, we have chord AQ that intersects with chord CP at point D. And therefore, we can definitely implement here rule 11. According to rule 11, we get that AD times DQ equals to CD times DP. Again, AD times DQ equals to CD times DP. And again, according to rule 11, AD times DQ equals to CD times DP. AD is 1, DQ in total equals to 1 plus 2, that is 3, and it is equals to CD. CD is the missing sign, so we leave it as it is, times DP. DP is equal to 5. So in total, according to rule 11, we should found out that 1 times 3 equals to CD times equal to 5. 1 times 3 is 3, so 3 equals to CD times 5. Or CD, Again, 1 times 3 is 3, so 3 equals to CD times square root of 5. Here we divided this equation by square root of 5 and finally found out that CD equals to 3 over square root of 5. So actually, the missing side CD equals to 3 over square root of 5 units in its length. Okay. In the next step, I copied the right again triangle DCB in a new page and we implemented the Pythagoras theorem on this again right triangle DCB in order to find out the length of the missing side CB. The again right triangle is the error that we are looking for. The error of the again triangle is the error that we are looking for in this question. So actually, this is the again right triangle DCB that I copied from the original drawing. We already found out that side DC equals to 3 over square root of 5 units inside, and the hypotenuse DB equals to the square root of 5 units. So according to the Pythagoras theorem, in this right triangle DCB, DB square equals to DB square equals to DC square plus CB square. Repeat again, DB square equals to CD square plus CB square. DB is square root of 5, therefore DB square is square root of 5 squared, that is 5, plus CD square. CD is 3 over square root of 5, therefore CD square is 3 over square root of 5 square, plus CB square. CB is the missing side, so we leave it as it is. So 5 equals to 3 over square root of 5 equals to 3 squared, that is 9, over square root of 5 squared, that is 5. So in conclusion, we found out that 5 equals to 9/5 plus CB square. Here we subtracted 9/5 on this equation, and finally found out that CB square equals to 5 minus 9/5. Here we multiplied 5 by 5 and then we divided by 5 in order to overcome factor with 9/5. And we found out that in the numerator, after we multiplied 5 by 5, in the numerator in total we have 5 times 5, that is 5 minus 9 over 5. So we found out that 25 minus 9 over 5 equals to CB square. 25 over 5 is 16, so in total this expression equals to 16/5, so 16/5 equals to CB square. And again, we found out that 16/5 equals to CB square. So here we took a root out of this equation. And found out actually, so CB square equals to 16/5, we took out of this equation and I found out that CB equals to the square root of 16, that is 4 over square root of 5. So CB equals to 4 over square root of 5 units in its length. This is side CB, this equals to 4 over square root of 5 units in its length. The next step, I copied the right triangle DCB in a new page and found out the area of this right triangle DCB, that is the area that we are looking for in this question. So this is the right again triangle DCB that I copied from the original domain. There, what is the area of this triangle? Actually, the area of this triangle is the area of the ring shape. But the area of n triangle equals to the base of the triangle times the height of the base over 2. We took the base as DC, therefore the height to the base is CB, because CB equals to 90 degrees with the base. Therefore the height is CB over 2. The base DC equals to 3 over square root of 5 times the height CB, that's equal to 4 over square root of 5 divided by 2. So here we have 3 times 4, that is 12, and square root of 5 times square root of 5 is 5 divided by 2. So in total this expression equals to 12 over 5 over 2. 12 over 5 over 2 is 12 over 5 times 2. So it is 12 and 5 times 2 is 10. So we found out that the area of the green shape equals to 12 over 10 square units. We divided both the numerator and the denominator of this number by 2. 12 over 2 is 6 and 10 over 2 is 5. So in total we found out that the area of this green shape equals to either 6/5 square units, or in terms of numbers, 6/5 is 1.2. So the area of this green shape equals to 1.2 square units. Okay, or we can say also that the area of the green shape equals to 6/5 square units. Okay, thank you very much.